All right, hey everyone. Hope things are going well. We're back with another of the live streams today, so that's pretty exciting. Yeah, so today we're going to be doing some circuit modeling, which should be a good time here. So the circuit that I'm working with is going to be this guitar pedal called the Crowther Hot Cake, and we'll dig into that a little bit more. And this is all going to be part of this plugin that I've been working on for a while here, the Build Your Own Distortion BYOD pedal or plugin, which has a lot of guitar pedal models and other guitar-centered effects internally. So yeah, we'll be working on that. We'll be getting into some wave digital filters and things like that. Is it possible to turn off this thing? There we go. That's better. Yeah, so this is BYOD. It's all on GitHub. It's all open source and open to contributions and whatnot. If anyone feels like maybe they have something that they would want to add or have be improved or a little bit different about it. Yeah, I haven't been working too much on it lately because I've been focused on some other projects, but I'm hoping to get a new update ready maybe sometime this summer, which should be exciting. And yeah, so I've started setting up some of the code for this model. I'll make the fonts a little bigger, but basically all I've done so far is just kind of set up the framework for basically having the model in the plugin that we're going to see in a minute here. So I'll show you guys what that looks like after I make this bigger. Oh, I missed a CMake change that I need to make here. So I've got to add the pedal CPP file to our CMake configuration. So let's go ahead and do that. I guess another thing I should mention is that I don't think I'm allowed to actually use the name Hot Cake in my pedal, because I'd imagine that's some, the name is in some way owned by the people who make this pedal, or at the very least, the model that I'm making is not sponsored by them in any way. So I don't want to give people the wrong idea about anything like that. Like this is the name of the pedal, and the thing that I'm making is just a model of the pedal. It's not sponsored by the folks who actually make the pedal, so I want to give it a different name. So for now, I've gone with Flapjack. I don't know if that's the best name, but hopefully that's good enough for getting around any potential intellectual property concerns. And so what we've got here is this circuit, this kind of an interesting circuit, and we'll dig into some of the specifics in a minute here. I guess I should close my window. We got some noise outside. Okay, sorry about that. Yeah, so we've got the circuit here that we're going to be modeling, and it's kind of an interesting circuit. So it seems like the primary distortion generator is going to come from this op-amp clipping here, and then we've got this funky transistor up here, which we'll have to dig into that one a little bit soon enough. And then we've got some controls. So we've got this drive control that seems to just control the level at which we're driving this op amp. We've got this presence control kind of on the output here, and then we've got the output level, which should be easy enough to get that parameter working, since it's just an output potentiometer basically. Yeah, and so let's go ahead and add these parameters while we're waiting here. So let's see if we can create a percent parameter. So this is going to be the drive parameter, and we'll default to 0.5, probably is the way to go. And then these other parameters, I think probably going with 1% is the way to go as well. So let's just go ahead and do that. So if I could spell presence, right? Oh man, my spelling's so bad today. Presence, that's still wrong, isn't it? I have an extra C. And then level. There we go. And then we're going to need those parameters here as well. So let's get those working. Float parameter. Presence, I think I got it right that time. I should set these equal to null pointer. And then finally, we've got our level param. And then, yeah, here in the constructor, we should set our parameters as we would with the usual sort of value tree state kind of parameter plugin setup here. So that's I've mostly switched away from using the audio processor value tree state in my newer plugins, but this plugin is still on the value tree state. And I had considered trying to get rid of it, but there's just so much code written that way already that it would be a pretty big endeavor to try to get rid of it. So I figured I'd not do that for now, at least. Yeah, but so that should be good to go. It's going to take a minute to build since I need to do a full rebuild. But yeah, once it's built, we should be able to take a look at it and get a sense of what it's going to look like within the plugin. But while that's building, let's start to think about this circuit a little bit more. So actually, I should mention as well that I got the schematic from this website. This is Aeon FX. I don't know if I'm pronouncing that right, but they have a number of interesting articles and other things that they work on. They build their own pedals. They sell these kits, all kinds of stuff you can get from Aeon FX. This article here is talking about the pedal, the Crowther hotcake, and talking a little bit about the history of the pedal and some of the ways in which it's evolved over the years and some of the different controls that have been added to it. And then kind of what they're showing here is that he actually took the circuit. So this is the PCB from the original pedal. And then he had to, this is called degooping. So some pedal manufacturers will put all this kind of plastic goop over the components in their circuit so people can't figure out what they're doing in the circuit. And so here he had to degoop the circuit by basically trying to scrape off all this plastic. And yeah, as you can tell, it looks like some bits of the circuit maybe got damaged a little bit, but that's just kind of part of the deal, something you have to deal with if you're working on that kind of thing. Yeah, and so at the end, he ended up with this schematic here, and that's what we'll be working with today. And so this section up here is basically just the power supply that's going to be supplying power to these other parts of the circuit. So for example, we've got VB, which appears to be a kind of bias voltage, and that comes from the VB spot on the power supply here. We've got VA, which is the sort of the op amp, like the positive rail for the op amp. And then we've got this VC, which is kind of doing interesting things. We'll have to talk about that a little bit more in a minute. And then, yeah, this system here is a bit strange, and I'd never seen something like that before, and I felt a little bit better because as I was reading this article, it seemed that the fellow who was doing the trace for this pedal seemed to have the same experience, where it's like, oh, that's kind of a weird thing that I haven't seen before. And so the idea here seems to be that this pin 5 in the op amp is a what they call the null offset pin. I'm not 100% sure what that stands for or what that means exactly. But according to this fellow and some of the conversations that he's had, it sort of softens the clipping. So as the voltage approaches the positive rail, it kind of gives it more of a soft clipping characteristic rather than the kind of hard clipping you would usually get with a usual op amp. And yeah, so you kind of get this weird behavior, but you also have this mode switch up here. And when the mode switch is in this setting with this 2 connected to this position 1 up here, this actually shorts out the Zener diode Z2 here. And that means that VA and VC have the same voltage. So basically the positive rail of the op amp will be the same as the base voltage of the transistor here. And so that's going to give us effectively the same result as if the transistor wasn't here at all. So the effect of the transistor may or may not be actually there, depending on which setting this switch is in. And we've also got this other switch here, which basically activates this parallel capacitor. But we can deal with that pretty easily in our model, so I'm not terribly worried about that. But yeah, so what I'm thinking, because some of the nonlinear stuff going on in the op amp here might be a little bit complicated. So what I'm thinking I should do is just simplify the problem first, try to solve a simpler version of the problem, and then work towards the more complicated version. So I think what I'm going to do is just try to pretend that everything is linear and come up with a model of the circuit that works that way, and then see where we can add in some nonlinearities to try to match the same type of response that we would get from the actual circuit, or maybe even come up with some new nonlinear behavior that would give us an interesting result. So yeah, that's kind of my idea here for today. And yeah, we'll see how much of that we get through. I'm not sure we'll get through all of it, but hopefully we'll make a good amount of progress here. Cool, looks like our build has finished. So let me remove the existing build in case there's any conflicts there. And copy the new one. But I need to do the -R. There we go. And so now I should be able to load the plugin and see the new pedal in there. So here's BYOD. And if I go into the drive menu here, there's our flapjack pedal with our parameters. Nice. That's good to see. I'm not 100% sold on these colors. Maybe we'll change those later. But yeah, that's kind of our starting point. So this is our basis for where our model is going to go. And yeah, I'll just put a little signal through it so that you can see that for right now, it's doing nothing. Yeah, so maybe this is a little bit small, but I'll make it a little bigger here. Yeah, so at the moment, the pedal is doing absolutely nothing because we haven't put any DSP code in yet. And that's what we're going to be doing here in a minute. So I think I'm going to use the wave digital filter method for modeling this pedal, partly because I think it will make sense. I think it's a good approach for this circuit, and partly because George has been asking me in previous weeks to talk about wave digital filters. So this will be a good excuse to do that. So I'm going to have to do a bit of work to get this op amp circuit working in the WDF framework. So let me do a little bit of drawing here. Try to do a little whiteboard kind of thing here, and maybe can I actually just drag the circuit in? That would be nice. What's it called? Screenshot. Yeah, let's see if we can get a screenshot of just this circuit here, and then pull that into our whiteboard. Does that work? Maybe not. Weird. Okay. Well, maybe I'll need to redraw it. That's okay. But yeah, let me get my drawing set up here. So, I'm not sure we need to deal with this resistor here because it's a 2 mega ohm resistor, so that's large enough that we can maybe just ignore it, since it basically operates as like a short at that much resistance. So yeah, well, I'll remove it for now, and then we can bring it back in later if we feel that we need to. So yeah, let's do this. So we've got our pen here. There we go. So we've got our VN. Oh man, that's a bit ugly. Let's see if we can do better than that. So we've got our input voltage. Oh man, all right. Wow, my pen here is giving me some trouble. All right, hopefully that's good enough for now. So we've got our capacitor, we've got our resistor coming down from there. We've got another resistor, and then we've got our op amp. I'm just gonna ignore all these extra pins on the op amp for now, and we can come back to that. And then down here, we've got this chain of capacitor and 2 resistors, basically. Capacitor, and I'm just going to draw it as 1 resistor since we're going to combine them in our model anyway. And then, yeah, on the output, we've got these 2 resistors feeding back to the input. Yeah, sorry, this drawing's a little bit ugly. The pen that I'm using here seems to be giving me some trouble today. And then let's see, here we've got kind of a strange chain of things. So we've got a capacitor. We've got 2 capacitors going to ground and a resistor in between. So I'm actually going to draw the capacitors going up. I think that'll be a little bit easier to see. Man, this drawing is a bit of a mess here. Sorry, guys. Let me see if I can clean off my screen here, if that makes things better. All right. All right, well, maybe it's a tiny bit better, but not a whole lot. Wow, yeah, this is really messy. Sorry, guys. And then maybe we've got our other resistor here, and then we've got a capacitor and resistor going to ground. And then, yeah, finally, we've got our capacitor and resistor going to ground at the output there as well. Yeah, and there's our very ugly circuit schematic drawing. Oh, you know what? I should have just done this from the beginning. All right, let's try this one more time. All right, so let's wait for it to save this time. And I'll just add a new thing here that we can draw on. There we go. Yeah, that's much better. Okay. Cool. Yeah, this will be a bit easier to see here. Right. So the way that we're going to do this is we're going to have to split this up into a couple of different wave digital filter kind of trees, like subtrees. So the way this is going to work is that our root adapter basically is going to be this kind of bigger adapter that handles all of the op-amp inputs and outputs. And then we can use an op-amp macro model to model the behavior of the op-amp. And then what do you call it? The subtrees will all kind of flow down from there. So let's see what we've got here. Actually, maybe we need a new thing for this. Well, maybe not. So we're going to have a node for ground. That's kind of the first node that I always think about. We're going to have a node for the positive and the negative terminals of the op-amp, and then we're going to have a node for the output of the op-amp. And I have a numbering system that I usually use. Let me grab my notes to see how I've done this before. Yeah, just so I can stick with my usual numbering system. Okay, so I usually actually flip it. So I usually have the negative terminal of the op-amp above the positive, but it doesn't matter so much. Doesn't matter so much here. So basically, we're going to have the positive op-amp terminal be node 2. So ground is usually node 1. So we'll stick with that for now. So this node here is going to be node 1. Oh man, come on. Why can't I draw on this today? All right, that's node 1. Positive terminal, so that's up here. Oh. It's going to let me draw on the image here. Okay, and lets me draw up there. There we go. So this is going to be node 2. And then this node here is going to be 3. yeah, again, apologies for the somewhat messy work. And then the output node, so that's right there, is going to be node 4. Right. And then the question is, do we need any other do we have any sort of unadaptable architectures anywhere else? And the answer, I think, is going to be no, because basically this resistor and this capacitor are in series. We're going to ignore the output resistor for now, and I'll explain why in a bit. So that's going to be in series. And then we're going to have these two are going to be in series as well. So that, yeah, the rest of that input stretch is going to be a little bit interesting. So yeah, we'll maybe come back to that in a minute. Oh, and that's kind of interesting too. Apparently the C5 is emitted here, so maybe we don't need that one after all. But yeah, so actually, I think we are going to need another node. This node here looks like that's going to be potentially important. Yeah, it's going to be kind of interesting because here we have a bunch of series elements going from node 3 down to ground, which is node 1, right? Then here, well, yeah, we might need a node there as well, because that's we have a connection from 4 to the end of R6. And then from that node, we have ground again at the bottom of this C6 capacitor here. And then we've got a resistor going to this node, which is the middle of our potentiometer. And then from there, we have another node going to that node there. So I'm going to need to start numbering these. So this one should be 5. And this node should be 6. And then let's see. I'm not sure if we're going to need to number this node or if we're going to be able to just kind of use it as a combination of the other nodes. Interesting. You know what? I think we are going to need to number that node. So this will be node 7 over there. So yeah, so we've got 7 nodes. And so now we need to think about the kind of the things connecting the nodes. And this will be done using a basically what they call Thevenin equivalent circuits. So some of you may have seen these before, but in case you haven't, Thevenin equivalent. So yeah, basically the idea behind a Thevenin circuit is that you can replace any number of sort of otherwise connected circuit elements, as long as they're linear and whatnot, with this resistor and voltage source equivalency. And so this is like an example of going from, a larger network of things down to just the resistor and voltage source. So that's basically what we're going to do, but we're going to do it in a form that we can use to generate a scattering matrix for the op-amp adapter that we're going to use in our circuit. So let's see here. I have a little repo that I've used for this before. I should close some windows here. So let's go to, I think this is in Yeah. So this is basically what the kind of netlist looks like that we're going to be working with. So I'll copy this as our starting point. So we'll call this txt. And so we can use the same set of things for the op amp here. So this is our E1, which is the op amp. So that goes 2, 3, 4, 1 as our same points that we had here. So 2, 3, 4. And then the 1 is kind of this internal thing within the op amp model. So we don't have to worry about that at the moment. Yeah, so let's get rid of these for a minute. So right now we have 7 nodes in our model, and we're going to need to add some internal nodes between some of the Thevenin resistors and Thevenin voltages. And there's not really a specific way that you have to do this, but I have a way that I've used in the past that seems to work pretty well. So I'll show you guys that. So the first thing that I've used here, oh, here we go. Yeah, so I can draw little hover things here. The first node that we're going to transform into a Thevenin and Thevenin equivalent circuit is this kind of stretch here that goes from node 2 to node 1. So this is going from the positive terminal of the op amp to to ground through the input voltage source, basically. So the way that I do this is I count how many nodes I've got in the circuit, which right now is 7, and I add 1 to that, and that's going to be my starting point here. So this is going to be 8 and 1, and then the other terminal is 2. So this will be 8 and 2. So this is the network with our input voltage is going from 2 to 1 through node 8 is kind of the way that I think about it. So I've got 2 and 1 and node 8 in between. The polarity does matter here, but we can tweak that later if we need to. Yeah, actually, maybe I'll just tweak it now just to be safe. So yeah, 2 and 1. Next, let's do this network here from 3 to 1. So this stretch of components here. So for that, we can do the exact same thing. We're just going to need to add 1 to the letter and to the internal node number. So this would be 9. And then this is going from 3 to 1. And this will be our drive, I'll call it, since it's the network that has our drive potentiometer in it. I don't know, maybe there's better ways to name some of these things, but that's how it is. Kind of next, I think we've got this 100K resistor, which goes from node 3 to node 5 there. So let's do that one next. So we've got VC and RC, and this is 10 here. And this is going from node 3 to node 5. So 3 to 5, and this is R3 is the component that we've got there. So there's kind of a systematic way that you can do this once you've split up the circuit in this way. And that's kind of what we're going to build on here. So next we've got node 4 to node 5, which is R5. So this is going node 4 to node 5. Yeah, so this is going to be kind of a big scattering matrix, so it may take a minute for it to generate. So I'm going to try to get this this netlist worked out pretty quick here. So then we've got 4 to 6 for R6. to output of 6. Cool. All right, so we've got that one taken care of. Next, let's do our C6, our C6 one. So we've got VF here, and this goes from 6 to 1, 6 to ground, 6 to 1. This is capacitive 6. So now we've got node 7 in the mix here. So we're going to have one part of the potentiometer going from 6 to 7, and the other part going from 7 to 5. You see kind of through that node here, because this node is node 5 as well. So we've kind of got two nodes worked out there. So first we'll do VG and RG. And this will be 14. And this is going to go from 6 to 7. And so this is going to be R presence. I can spell it presence P. So P is for plus, and then the other one's going to be M for minus. GH is next, yeah. And this one's going to go from 7 to 5, we had said. Cool. And now we've got 2 more. So this is actually just 1 more. So these 2 are in parallel with each other because they both go from 7 to ground. So that should be our final node here. So this is I guess, VI. 16 goes from 7. This is going to be, I'll just call it V out. Or I. Actually, I might have to be careful with the label RI here. I'll talk about that in a second. So this is going from 7 to 1. And that should work. Yeah. So the problem here is that the op-amp model also has a thing called RI in it. So I need a different letter here. RJ. I don't think anyone else is using RJ. So let's give that a try. And so here we've got our netlist for our circuit here. I wish we could simplify it a little bit because it's kind of a heavy netlist at the moment, but I don't think, I don't see an immediate way to do that at the moment. Yeah, I can give it a try and come back to it. So yeah, what I've got here is, and the rest of this folder is a Python system using the Sage Math tool to calculate the scattering matrix from this netlist. But recently I've been using Mathematica instead. So let's give the Mathematica one a try. I think it's a little bit more powerful. Okay, cool. We've got a question here. Let me finish logging in first. Oh, come on. Oh, there we go. Must have just typed it wrong. So we want the RSolver notebook here. And then I've got a folder for netlists. So let's upload the file there. Digital filters, RSolver, no scratch. This is our hotcake. file up there. Cool. So I'll get this started, and then I'll look at the questions that we've got here. Okay. Cool. Yep. So there's our netlist. Now Mathematica is going to parse the netlist for us. That looks good. It's going to construct a modified nodal analysis matrix, which we can see here. Yeah, that looks about right. So now we're going to remove one node from the matrix just because the system is overspecified as it currently stands. So we're going to get rid of this column and this row. And now we've got this matrix left over. This is a 25 by 25 matrix, which is a bit of a large one. So let's see how long it takes for Mathematica to invert that matrix. Oh, actually, I should have fixed this before, but it's okay. I can do it later, I think. Yeah, so I have a parameter here for which port we're going to adapt. In this case, we don't want to adapt a port. So I may have to hard code something in a minute here, but we'll wait until this step is done. So yeah, okay, let's see what questions we've got. So Jazz saying, doing a single op-amp buffer is okay, but is having a circuit with more than one really viable? I heard Andrew Simper talk about how the lookup calcs increase exponentially when you have more parameters. Yeah, so I mean, I guess it kind of depends too on how you're treating the op-amps. So if you're treating the op-amps as linear elements, which we are doing for now, but I think I mentioned this early on. For now, we're treating the op-amp as linear, and then after we've got the linear model working, we're going to go back and see if we can get a nonlinear version working. So if you're treating the op-amp as linear, then having more than one really isn't too bad. You just end up with bigger and bigger scattering matrices. And you don't really need lookup tables if you're doing that as well. You can kind of get around it. But if you're treating the op-amps as nonlinear, then yeah, you definitely the complexity is definitely going to increase pretty quickly. For the reason that Andy mentioned as well. I know Andy also has some method. I think he's talked about this at some point of kind of splitting up some of the lookup work into different tables, but I don't think he's published that anywhere just yet. But that'd be cool to see at some point. Oh, okay, and then Jess is also asking about an input resistor. Yeah, so I should have mentioned this actually. So this is a little bit of kind of a cheat that I've done from time to time. So for an ideal voltage source in a wave digital filter scenario, you would have to adapt the whole model to work with an ideal voltage source, which is kind of similar to a nonlinear element from the perspective of wave digital filters. But in this case, I'm kind of cheating and just pretending that we have like a really small input resistor that's more or less negligible. Is that kind of the question you were asking? I'm not 100% sure. Yeah, I'm not 100% sure what the idea was there. Okay, did that finish? It seems like it maybe didn't finish. Okay, interesting. Let's maybe try the next step here. See if maybe that'll work, or maybe it's still waiting on the previous step. I'm kind of under the impression that it didn't finish inverting the matrix. Yeah, 25 by 25 is a pretty big one. I was talking about RI, that is supposed to be the input resistance. Yeah, so that's I don't know, maybe I should be a little more careful about some of the naming systems that I use here, but basically RI in the op-amp macro model is treated as the input resistance for the op-amp. I guess this also kind of assumes that if you do have a circuit with multiple op-amps, they all have the same input and output resistance, which may not be true, I guess. So yeah, maybe I should fix that up and be a little more careful about it. let's see. Yeah, so RI is input resistance, but input resistance for the op amp, not for the circuit as a whole. All right, let's see. This is taking a little longer than I had hoped. Plus, I'm not sure that we actually finished doing the matrix inversion. So maybe let's start over here and see if I can get it working better. Okay, so it did abort. Okay, yeah, maybe I just need to give it more time then. And hope it doesn't time out or something. Yeah, I tried one previously with this drum circuit, and that one, I remember I got that one to time out. But I think that was a smaller one. But anyway, maybe let's come back here while that's spinning and see if there's a way that we can reduce the complexity of this model a little bit. Yeah, maybe we can remove some of the Thevenin or some of the voltage source nodes from the Thevenin equivalent, since we've got these 3 resistors here that maybe don't need the Thevenin voltage source. Yeah, and having to do two separate ports for both sides of this presence resistor is not a lot of fun either. Oh, and actually, I messed something up here because I should have another what do you call it? Another port for this output network here. Yeah, because I had assumed that would be in parallel with this network here, but that's not totally true because there's this separate port internally there. So for now, I'll just fix that here. So this is C7 and R7. Yeah, so this makes our netlist even bigger, which is potentially problematic. And this one goes from, well, how did I label these? So that's 7 and that's 5. Oh, okay, I see. So this one actually goes from 5 to 1. And this is our output network going from 7 to 5. Okay, so yeah, I'll need to redo this as well. So let's abort our evaluation. Let's delete this file and then upload the new version. Oh, what's going on here? Why are our files missing? There we go. And this is the new version. Cool. Yeah, so let's try this again. I'll set that correctly this time. So we'll parse the netlist again. This time we've got a couple more elements in it because of the mistake that we just fixed. So we've got an even bigger scattering matrix here. Yeah, so that's 27 by 27. That's going to be a pretty big task to invert, but maybe let's get it started and see if maybe it can do some work for us while we're waiting. Yeah, but I'm thinking that we may be able to get rid of some of the Thevenin voltage source nodes. For example, this R3 node here, right? Do we really need a voltage source and an equivalent resistance? You know what? Let's try it. I'll make a copy here just so that we don't overwrite our work. So this is hotcake. I'll call it hotcake simplify. So what we're going to do is whenever we have a port that is just a resistor, we're going to get rid of the voltage source in the Thevenin equivalent circuit. So here we have R3, which goes from 3 to 5. So we're just going to have that all be handled with this resistor here and get rid of the additional node that we had there. And we can do the same thing with R5 and R6 and with the R presence thing. So R5 goes from 4 to 5. R6 goes from 4 to 6. R presence P goes from 6 to 7. And then R presence M goes from 7 to 5. Is that right? Yeah. That is right. And so now we can actually simplify or reduce some of these other numbers here. So this goes down to 10, 11, and 12. 10, 11, and 12. So that should work out as a simplified netlist here. Let's see how far mathematics has gotten. It seems like it hasn't gotten very far. So let's, oh, it's up here. Why did it, oh, interesting. I guess it never started on that one. That's okay. Let's get our new netlist in here and try that instead. So this is the simplified netlist. And see what you got. All right, that looks decent. Okay, so I had this assertion here to check that we have the same number of voltages and resistors, but I've made it so that's no longer true, but let's see if that's okay. One thing I really wish Mathematica had was a way to comment out a line of code, because now I have to remember to put that back when I'm done here, which could be difficult if I don't remember. But yeah, so now we've got our scattering matrix, which is 18 by 18. So that's much more manageable, hopefully. And actually it's going to drop to 17 by 17 once we get rid of that extra node. And yeah, now let's invert. And hopefully this doesn't take too long. I think the last one I did was 15 by 15, and that one took somewhere around a minute, maybe a little bit longer. So yeah, we'll probably be waiting here for a couple minutes if folks have questions or other things they're concerned about. I'm gonna drink some water. Wow, no questions. So everything I've done so far makes perfect sense to everyone, I guess, if there's no questions. I haven't made any mistakes or said anything confusing. Wow, that's amazing. Okay, John says, I think I still like to stick around at separating nonlinear circuit from linear circuit as it's way faster. But I know that it sounds drastically different if you don't separate them. Yeah, I mean, that's true. I guess it also, I think I talked about this a little bit last time. It also gets kind of depends a little bit on what you're going for as far as if you're going for an exact replica of some sound or some hardware that exists and then how it sounds, or if you're going for more of a, a new creative effect of some kind. But yeah, I mean, hopefully we'll have time to get to this today, but that's kind of what I was going to try to get into, was thinking about how we can make this sort of transform this linear model into a nonlinear model, and maybe how we can get creative about that. But yeah, I don't know if we'll have time, just depending on how long it takes to get the linear model working. But yeah, I mean, the other kind of way you could think about it is that from sort of a more purely mathematical sense, it should always be possible to separate the linear and the nonlinear circuit elements, or separate more generally like the linear and nonlinear parts of your system. And kind of the proof of that is the idea of the Wiener-Hammerstein models, and how effective those can be. So, I mean, if you think about it sort of from this more purely mathematical standpoint, you should always be able to get the right thing, or the correct output from your model, even with completely separate linear and nonlinear parts of your model. It's just a question of going through the other steps that you need to get the linear and nonlinear parts of your model correct as separate entities. Whereas I guess when you're working in a white box model kind of situation like this, then maybe it's a little bit easier to kind of keep everything cohesive and all together, which lets you reason about it kind of in the same way that you would reason about the original circuit schematic. And you kind of lose that if you try to separate things too far. But yeah, I mean, it depends on the system that you're modeling. It depends on what you're trying to get out of your model, and so on. So yeah, it's a good question. All right, looks like we still don't have a answer yet. It's been maybe 3 minutes. Maybe I'll try my Python solver in the meantime. And see what I get from that while Mathematica is doing its thing. Let's see, what have I changed since my last bit of stuff? Okay, let's see. So I may need to remove a similar check as I had in the previous one, where I was checking that we had the same numbers of resistors and voltages. So yeah, I'll comment that out for now, and we can bring it back later if we need to. And then this is the command that we can use to run the solver script. So the netlist that I want to generate a matrix for is the hotcake simplify. And now I also need to look at my other arguments. So let's see. The datum node can be 0. That's fine. We don't need to do anything with that. We want to adapt. Okay, we don't want to adapt a port, so we can just use the default argument for that. And we want to output to Scratch, and we'll call this hotcake scat.text. Actually, I usually do uscat to specify that it's an unadapted scattering matrix. And we'll do verbose. Yeah, let's give that a try. So we're having a bit of a race now, Mathematica versus Python or versus Sage Math. Oh, okay. Mathematica has run out of computation time for the Wolfram Cloud. So I could try running it locally as well. Maybe I'll do that. But maybe let's give the Sage solver a shot. So here it's spitting out the same matrices that we saw from the what do you call it? From the Mathematica output that we had here. So this bunch of text here is the same as the bunch of text here. It's just formatted a little more nicely in Mathematica. Yeah, so now it's inverting, and we'll see how long that takes in Sage. Yeah, so then I guess the next step, if this is taking too long, is we can also see about simplifying things a little bit further. Yeah, let's think about this. Seems like the Mathematica server CPU is sweating. Yeah, it does. But it'll be my CPU sweating soon enough if I decide to try running it locally. So maybe that's the fair way to go as far as some of these comparisons as well. Yeah, so I guess the other thing that we could do is just try to take some of this output network and make it a bit more sort of separated from the op amp side of things. So maybe think of this more as like the drive circuit, and this part more as like the tone circuit. Yeah, that could work, but then we would need to figure out kind of what loading effects we would have between these two sides. But it's possible. Yeah, so I guess the trick would be we would need to figure out the impedances that, for example, this 10K resistor would be facing downstream. And then maybe we could treat that as like a load resistor for the output of the op amp stage. But then I guess we still have this kind of intermediate voltage that is interacting with the presence, the other side of the presence potentiometer there. So that might be a little tricky. Okay, we did get the matrix inverse. I probably shouldn't have tried to print it because that's gonna take a while. Interesting. Okay, so Sage performed a little better than Mathematica did as far as getting us the matrix inverse. However, the part where I know Sage has trouble sometimes is with simplifying the matrix. So we'll see how that goes. Yeah, I really should not have done this in verbose, in the verbose mode. That was a poor choice on my part. Oh man, yeah. Why did I do that? So yeah, this is the fun of doing circuit modeling, is you get to see the computer do way more math than you would ever even consider doing by hand. Yeah, that's a pretty insane matrix inverse. Oh man, yeah, it's still going. Wow. Yeah, so you can imagine why it's going to take probably a little while to simplify the matrix from there. Anyway, while that's going, maybe let's try local Mathematica and see if that does any better for us. Okay, so now we've got some problems. So we're trying to diagonalize. Oh, interesting. Okay. Interesting. Okay. Yeah, so we need this RP diagonal matrix to be the correct number of the correct size, which we might be screwing up by getting rid of those voltage source nodes. Let's see, where do we decide how many ports we have? Num ports. Well, I think that's oh, I see, that's a parameter here that comes from there. Num ports comes from num voltages. Interesting. Maybe I should do num resistors instead. But I worry that that's still going to cause problems with the matrix sizes. Let's see. So we've got ourselves down to this 17 by 17 matrix, and that's going to be the same no matter which, no matter whether it's the original matrix or the inverse matrix. And then let's see. Yeah, so we're trying to construct this. We're trying to construct this matrix here, but let me just try something. Instead of X inverse, I'll use X matrix. They're the same size, so it shouldn't matter. And then instead of num ports, I'll do num resistors. So that gives us a 10 by 10 matrix. And then let's see, what do we actually need this for? I wonder if we only need this. I wonder if we only need this when we're trying to simplify, or sorry, when we're trying to do our adaptation. That might be the case. Let me double check against the Python version. Well, maybe not. Let's see. Adapt port. Well, let's see here. Scattering matrix RP. That comes from this compute S matrix function. Oh, I see. Okay, so to get the matrix, we need this. To get the final scattering matrix, we need this equation here, right? So we have our X inverse matrix here, and in this case, oh, it's also called X inverse in the Mathematica version. So you have this X inverse, and we need to multiply it through these set of things. Let's see if we can get the right dimensions just doing it that way. So I'm going to get rid of the inverse for now, which is stupid, but whatever. We can bring that back later. Again, comments would be helpful, but I guess that's just not the Mathematica way. So here's where we adapt the scattering matrix, but that's not actually what we want. Oh, you know what? That seemed to work because we computed the unadapted scattering matrix here. That seemed to do the right thing. Yeah, so we end up with this 10 by 10 scattering matrix. And if you look back at our netlist, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, we have 10 ports. So that should be the right thing. Okay. Let's give that a try. let's see, let's use local Mathematica this time, and see, there we go. Bring this back to what it was. So yeah, let's try this locally now. Oh boy. Okay, let's see if I can remember how to do paths locally here. Import. Okay, maybe it'll just work. We have digital filters, our solver, scratch, hotcakes, simplify, and what I need a close bracket and semicolon. Okay. So yeah, let's give that a try. So we got to start up the Mathematica kernel. Obviously, that's not going to work right now because we're running locally. And that seems to be the correct netlist. Now we've parsed our netlist and we've got our nodes. Now we've got our M&A matrix. Now we've got our datum node removed. Yeah, and now let's see what we end up with if our local Mathematica can fix this scattering matrix. Let's find out, or can invert this this matrix. Wait, did it just finish? No way. That can't be right. Something has to have gone wrong. All right, let's simplify and print. Oh, okay, no, it didn't finish. It's still running, which you can tell because of this handy running thing up at the top. I guess it just figured out what the dimensions would be and printed that ahead of time. Fair enough. Yeah, I wish it was a little bit easier to tell exactly where like kind of how much progress the thing had made, because this kind of made me feel like it had finished. But in the cloud version, I get this spinny thing here that tells me that it's still running. Anyway, while that's happening, maybe we can try to tweak this implementation a little bit so that it doesn't hit the same problem that it did last time. So when we're calling compute S matrix, we're using this numports thing. Numports comes from here when we parse the netlist. So yeah, if we're not going to have this be num voltages, maybe let's have it be num resistors instead. So something that could be kind of fun now, if I stop the Mathematica notebook and restart it, I could do an actual race between the Python implementation and the Mathematica implementation. But that might not be the best idea either, because they're both running on the same CPU at the same time. So they'd kind of be fighting each other for resources, I would imagine. Maybe that's not the smartest thing. I don't know. The Python one finished. I haven't seen the Mathematica one finish. So maybe I should just run the Python one for now. I'll give it another 2 minutes. Yeah, so this is the other part of analog modeling is you have to do a bit of waiting while you wait for your scattering matrices to compute themselves. But well, I shouldn't say they compute themselves because they don't compute themselves, but they have to. The system has to compute them for me. All right, I think the timer is almost up here. I'll wait until this clock hits 47, and then if it's still waiting, then I'll switch back to the Python version. Maybe I'll just get the Python version started and let them fight it out for the CPU resources. Yeah, I'll just do that. It's fine. 22 by 22. That doesn't seem right. Interesting. What did I do wrong here? Oh, you know what? Maybe this wasn't the smartest approach. It seems like it's giving me the wrong matrix shapes. Yeah, let me try this again. See if it'll finish up here. So I'm gonna run it in verbose mode again, but I'm not gonna print the X matrix inverse this time since that's part of what took forever last time. No. Wow, I really would have thought that Mathematica would be the faster one here. It's a little bit disappointing for me. Oh, I think I messed this up because I ran this cell twice without rerunning this one. So I think I need to abort this one anyway. Yeah, let's try this one again. Wrong thing. Yeah, there we go. So you've got our 18 by 18, and then when I run this cell, we get 17 by 17. And yeah, let's run this and see how long it actually takes to get our matrix out. Yeah, so how did I do this in Mathematica when I was constructing the X matrix? Okay, so I've got this num ports thing again. Num nodes by num ports. Interesting. Yeah, I must have done something a little bit different than I'm doing in Python. Okay, Jazz saying, did you ever thought of writing your own C++ circuit solver? It'd be more time consuming to write it, but it might come in handy. Yeah, I've definitely thought about it. Yeah, it seems like it's always seemed a little bit painful to me to use these systems like Mathematica and Sage when pretty much all I need is like symbolic matrix inversion and a couple of other little things. Kind of the thing that stopped me is that doing symbolic math in C++ in general seems like kind of a tall order. Yeah, I don't have a great grasp on how I would even get started with that. But yeah, I mean, that'd be a cool thing to do, definitely, if I could get it to work. It would definitely save me some time down the line with obviously a bit more time cost up front. But yeah, that's something I've thought about. Maybe I'll do that at some point. But for now, I'm okay with sticking with these tools that I can use instead. I don't know. Maybe if someone else has an idea for how that can be done more simply than with these tools, that would be cool as well. But also, I don't really mind. I don't really mind having a code generation system like this. So that's basically what I'm doing here. Is I'm generating a scattering matrix for C++ or to be used in C++. So it's basically code generation, and I think that in general is oftentimes a good approach for this kind of thing. Since I mean, you can do code generation in C++ too, but it gets a bit gnarly pretty quickly. And so yeah, this kind of code generation system I think is good overall. The problem is just getting it to run quickly enough to be helpful. But yeah, so I don't know how much longer I want to spend on this today. I've got a few other things to do this afternoon. So maybe this would be a good thing to pick up again in a future stream. I don't know. Let me try again to see if I can get the Python thing to work out. Oh, thanks, Josh. Yeah, thanks again for having me on. It's always a fun time talking on the stream and hearing people's thoughts and everything. Yeah, it's a bit of a bummer that Mathematica is not performing as well for me as I'd hoped. Yeah, let me see if I can get this working in Python real quick, and then I'll do that before. Let's see if I can do that before heading out for today. So xmat. Interesting. Okay, so the dimension we have here is this num nodes plus num ports plus num extras, and that's where we get our dimensions for xmat. Alternatively here, when we construct X matrix, what are we doing here? Construct X matrix should be the same, right? Well, I guess not, because here we set num ports equals num voltages. So that's a little bit different, yeah. Interesting. Yeah, this trick that I did to get rid of the extra voltage sources may not be a valid trick. In the end, I may have ruined some things that I would otherwise have needed to do. Interesting. Let's see. So num nodes plus num ports plus num extras. So what does num ports mean in this scenario? Or I guess how are we using it is really the question. So interesting. Maybe I need to be a bit more careful here. So let's do this. Let's do num voltages like we had it before, and then let's also return num resistors. And then when we use this function on the other side, we'll get the num resistors out. And then when we compute the S matrix, that's when we're going to want compute S matrix. That's when we're going to want it for creating this RP diag, thing. So let's see, num resistors, and that will be the thing we're calling here, the thing we're using here. Okay. I still feel like I'm missing something or I'm doing something wrong, but yeah, that may be just something I need to step away for a few minutes and come back to figure out. But that's okay. Yeah. Yeah. So maybe I'll try to get the scattering matrix figured out later, and then maybe next time I'm doing a stream or something, we can finish up this model. Although I was hoping to get back to the other plugin for the next one. But yeah, we'll try something real quick. So yeah, so let's see. Interesting. Interesting. I wonder. Anyway, let's give this a try. So I'm skipping the the matrix inverse part for now, just to see if we can get this to work. So I'm running it in verbose mode, but I'm not printing the inverse matrix. Oh, I see. I forgot to add my new argument here, num resistors. Oh. Let's try that again. Okay. Unsupported operand for parents. Full matrix space of 10 by 10 dense matrices over symbolic ring, and full matrix space of 5 by 7 dense matrices over symbolic ring. And that seems to be coming from here. Oh, wait, from here. Yeah, so this is a problem that we're getting when we, this seems to be a problem that we're running into when we try to get from our inverse matrix to our scattering matrix. So that means we have a dimension mismatch, mismatch. Yeah, I always forget how the order of operations works for this this kind of thing. I think it's left to right. So we should be doing this first, and then that times x inverse, and then that times vert ID, and then all that times 2, because 2 is a scalar, so you can put it on whichever side you want. Interesting. Let's see how Mathematica is doing. Okay, maybe it finished. Yeah, it looks like it finished. Okay. Let's see what we get here. This is definitely going to take a minute to simplify the matrix as well, but hopefully we should get an answer here. Although it's kind of interesting because this is the line where the Python implementation had the dimension mismatch error that we just saw. So the fact that we didn't see that error in Mathematica is a little bit curious. Interesting. let's try a couple other things here just to appease our curiosity. Let's try printing RP. Yeah, so that seems to be what we expect. Oh, and then I guess it doesn't like trying to simplify matrix. That's a bunch of, I think it's just the identity function or just the identity matrix. So maybe Sage isn't happy about that, but that's interesting. So we're getting the RP matrix that we're expecting to have. But for some reason, when we try to do this matrix multiply, someone's not happy. Yeah, interesting. There's something different between the Mathematica implementation and the Python implementation that I need to figure out. Yeah, I need to figure out what's going on here exactly. It might be something to do with this. I was doing these like negative indices, and then Python will wrap that around for me. And I think I had to do things a little bit differently in Mathematica, but maybe not. Anyway. Oh, cool. George is here. Yeah, so we're working on doing an emulation of the Crowther Hotcake guitar pedal. And this is the circuit that we're working with. And yeah, so right now, this is a good recap, actually. We've gone through kind of drawing out different parts of the circuit and constructing a WDF netlist for it. And then I'm working on this kind of simplified netlist that hopefully we should be able to compute a little bit more easily, or do a compute a scattering matrix for a little bit more easily. And now I'm fiddling with Mathematica and with Sage Math to try to generate the scattering matrix for me. And it's taking a little while, so I don't know if we'll be able to finish this one today, but we'll come back to it at some point in the future. Yeah, so interesting. Let's see if we can do some of these intermediate matrix multiplies and see if Sage is okay with that. Interesting. Okay. So apparently this matrix Sage, or this multiply Sage is not happy about, which is interesting. Full matrix space of 5 by 17. Why is it 5 by 17? Num ports. Let's see here. Maybe I did something wrong here. Num ports is 5. Okay, what if I do num resistors instead, just to make this guy happy? Yeah, at this point we're kind of into just hacking territory, rather than really doing anything especially useful. But maybe there's something that we can get out of this that might be helpful in one way or another. Yeah, what if I just use num resistors like everywhere that I was using num ports here? Let's try that, see what we get. Okay, so that seems to be the thing we would expect. And then let's see what we get. Okay, yeah, so it's an issue at the same spot, full matrix space of 5 by 5 dense matrices and full matrix space over 10 by 10 dense matrices. So yeah, we've still got a dimension mismatch somewhere in there. Somewhere in there, I have a way of printing the shape of the matrix. Let me see if I can remember how to do that. Okay, something like this. So let's see. Let's see here if I can print the dimensions of these things. So X inverse should be 17 by 17. We already know that. The vertical identity matrix should be 10 by 17, if I'm remembering right. And then for the horizontal identity matrix, I don't remember. Let's see what we get. So 10 by 17 and 10 by 17. And then, let's do the same thing with this one. This would definitely be 10 by 10, right? Yeah, that's 10 by 10. Okay, so what did we do wrong? Oh, we did the wrong thing here. I think that should do it. Nice. Okay, cool. Yeah, so right now it's not doing anything especially useful because I skipped the matrix inverse step. So it's just going to be something silly here. But maybe that'll work if I bring back the matrix inverse step. And then, of course, the matrix simplification step is going to take forever, even if I do get that working. As we're seeing here, even in Mathematica, it's taking forever. So let's see. Did I break anything else that I need to unbreak before I run it again? Let's see. Mostly just print statements, and some new arguments. Cool. Yeah, that should be fine. Let's give it a try, see what happens. What's the worst that can happen, right? Well, the worst that can happen is that my computer blows up from trying to run too much stuff at the same time. But if that happens, then so be it. Okay, George is asking, what are the full system dimensions? So actually, Mathematica shows this a little bit more nicely. So the MNA matrix, and again, this is a simplified netlist. We have a fuller netlist that has more stuff in it. But in the simplified netlist, the MNA matrix is 18 by 18. We've removed the datum node, and so that gives us 17 by 17. And then when we finish getting our scattering matrix in the wave domain, we'll have a 10 by 10 matrix, which will be pretty nice. So yeah, I'm looking forward to that if we're able to get it. But yeah, I probably got to run in a minute here. Just to get to some other stuff this afternoon. But yeah, we'll definitely come back to the circuit next week. I'm not sure I'm going to be around just because I've got some other things going on. The week after that, I should be back. Maybe I'll do more work on this circuit. I also kind of wanted to get back to showing some stuff with the plugin that I've been working on. Maybe I'll do a quick demo, actually, just since we're waiting for stuff anyway. Yeah, just for fun. But yeah, I wanted to continue working on the multi-tool plugin. But yeah, here I'll show a quick demo of something I was working on the weekend. But yeah, so I don't know, the next stream will either be more of this circuit or more of the multi-tool. But yeah, we'll definitely come back to this circuit at some point, whether it's in a couple weeks or maybe it's sometime after that. It's not going anywhere and I'm not going anywhere. So either I'll figure out the circuit or the circuit will figure out me, and that'll be that. Yeah, so this is the multi-tool plugin, and I was working on the wave shaper a little bit on Friday and on the weekend. So right now, this is just a regular TAN-H wave shaper, nothing too fancy. And we've got, our other shapes. So we've got our rectifier, we've got our, wave folders and things like that. But the thing I was working on, which I'm pretty excited about, is this free draw mode. So the way it works is you can go into draw mode. So when you're in this mode, you can control the gain as usual. But when you're in draw mode, you can go in and actually draw in your own wave shape and kind of do whatever you want with that. And so that's pretty fun. So yeah, this is our new free drawn wave shaper. And there's some anti-aliasing and other tricks going on in there that should help make it sound good. Although I guess, if you draw a crazy enough shape, it may not sound good ever, but that's just your choice as you're drawing it. So I'm pretty excited about that. And so, yeah, the multi-tool plugin will definitely be coming back to as well in a future week. So yeah, that's about all I've got for today, but let's check in one more time on our industrious solving tools. They're both still running. So yeah, it'll probably be, another, I would guess another hour before they're done. So yeah, I'm going to call it a day for now. And yeah, we'll pick this one up in a future stream. So yeah, thanks for tuning in, and I'll see you all a little bit later.